Good morning. Today I am telling on the Stereochemistry Part-3 and I am Dr. Suparna Rana, Associate Professor, Haldia Institute of Technology. And this is my third lecture and I am telling about the projection formula of the various types of compound. We can express the compound 3D structure into our board or say paper by the 2D manner. So that's why here I will describe that various types of projection formula, how we can write the compound into our 2D structure. So therefore we can express that the 3D structure. And next one, that is the Fisher projection formula. According to the scientist name, that the projection formula name are given here. So Fisher projection formula, Newman projection formula, Shobos projection formula, flying wedge formula, and the zigzag formula. Here mainly we discuss about the Fisher projection formula, Newman projection formula, Shobos projection formula, and how we can convert say one type of projection formula to the another. We are described here. Next one, Fisher projection formula. So when we write the Fisher projection formula, there is the requirement is the minimum one chiral carbon atom. Means the carbon atom which is linked with the 4 different group. So we can say this is the chiral carbon, and here requirement is the minimum one chiral carbon. That's why we can draw the Fisher projection formula. So when we draw the Fisher projection formula, so here you see that is a plus type of line, and here we are represent 3D structure to the, that is the Fisher projection formula. How we can write? So into the Fisher projection formula, the horizontal line that is up and the vertical line that is below. In this manner, if I represent the compound, so we can very easily draw the Fisher projection formula. So here I draw, that is the R-lactic acid, this compound. How we can write this one? So that's why here I will take the compound, that is the R-lactic acid, into the 3D structure. So we can express into the Fisher projection formula like this. So that's why here I will take this compound, and here this is the 3 different groups. One is the hydrogen, another is the OH, another CH3, and here it is COOH. So here it is below, and this is your up, and they are in the plane. So you can hold the functional groups in this manner, that which is up and down by your left hand and right hand. So in this manner I just take, and then if I take in this manner, so they are coming up and they are coming below. So we just represent that the upcoming group, they are into the vertical line, and which are the down, they are into the that is the upcoming thing, that is the horizontal, and the down group, they are vertical. So that's why if I represent, so our representation is this one, and we can also express that here this is our Fisher projection formula of the R-lactic acid, and it is a one chiral carbon atom. If it is more than one chiral carbon atom, so therefore that is horizontal line, they are up, and the vertical line, whole vertical line, that is below, and all the chiral center that can be represented at the point. Okay, so that's why we can express that the Fisher projection formula. Next one, that is the Newman projection formula. So Newman projection formula, when we can represent this one, so we must require minimum 2 carbon atom. It is chiral or achiral, that does not matter, but we must require that the 2 carbon atom which is attached to the different types of group. Say for example, here I take this compound, that is C1, C2 carbon atom, where C1 is the front carbon, where we are C here, and here we can represent the group into the various types of group here, that is the Cl up, H is below, and CH3 in the plane, and here it is say H is the up and Br is the below, and the OH is the in the plane. So now we can take here in this manner by holding the Cl group by the that is the up group by my right hand, and the below group, that is my left hand. So if you see in this side, from your side, this is your front carbon and this is your back carbon. So when we represent the front carbon by the point and the back carbon by the side circle, so the front carbon is attached with the 3 groups. One is the hydrogen, another is the Cl, and the third one is the CH3. And the back carbon which is attached here, that is OH, Br and H. So from your side, if you see into the Newman projection formula, so this is your point and this is the circle, so the another groups they are linked here. So we can express that the three-dimensional structure to the Newman projection formula in this manner. Next one, that is the Sawhorse projection formula. The term is coming from the Sawhorse, that is the table which is used by the carpenter on the carpenter table, that if you add the two groups and in which manner it is linked, we can express the molecular structure in this type. So we can say this is the Sawhorse type projection formula. Now here we represent the CH3H and it is CH3H. So here also that we are considering that the two minimum carbon atom. Next one, that is the flying wedge. So when we represent any flying wedge types of compound, so therefore any carbon atom which is minimum, it is linked with the four different groups. So here that the two groups they are in the plane and the other two groups they are, one is the up, another is the below. So that's why if I represent here this carbon atom, it is linked with the four different groups. Here it is this and this, that the two groups they are in the plane. So we can draw into the board, they are like a line, okay, and that one is the up, another is the below. So which is up, so we can represent by the wedge, and which is below, that is the dotted line. Okay, so in this manner we can represent that the flying wedge formula of the compound. That is how we can convert the Fisher projection formula to the Newman projection formula, and then it is the Sawhorse projection formula. So that's why as it is this one, so therefore we will take the compound which has that the two types of the two carbon atom, and here it is linked with the four types of that is the different types of group here. Now we can express this one in this manner. It is better to you. So here it is, if you see this compound, that is it is CH2OH. Okay, it is CH2OH, it is OH, it is H, it is OH, it is H, and it is CH2. Now, in the Newman projection formula, we can express this molecule in this manner at first. Okay, so when we can express, so this is our front carbon. So front carbon it is our that is dotted, and the back carbon that is the circle. So now we can express here. So in this manner, that's why it is below. In the Newman projection formula, that is your below, and these two groups is up. So in this compound, that is your up group. That is, if you see here, okay, this one. So this is your CH2OH, and this is OH, and it is H, and it is OH, H, and this is your CH2. Now we can express that is the Newman projection formula here. And next, when it is coming, so we will just rotate into the 180 degree. Okay, just rotate into the 180 degree, that is the back carbon. So we can also express this is this one. Now from here to here, when we can represent, so we must draw here that the eclipse conformer of this compound. Okay, eclipse conformer of this compound. If it is eclipsed, so therefore when it is the Fisher projection formula, that is your below, and this is also below, that CH2 is also below. So this is the below, and here OH, OH they are up, and HH also up, and there OH they are right hand side, and H that is left hand side. So here also into the Newman projection formula, we can observe the CH2OH and CHO. These two groups is below, and these two OH group they are up right hand side, and these two hydrogen they are up left hand side. So therefore we can express that is the D-erythrones into the Fisher projection formula, to the eclipse conformer formula, to the staggered means if you rotate the C2 carbon atom by 180 degree, then you can express this structure into the staggered projection formula of this compound. And in the same manner, that if you want to convert that is the staggered to the Newman to the Fisher, you can also do this one, but you must remember this one. When you convert Fisher to the Newman, you must take here into the Newman projection formula that it is the fully eclipsed conformer. You can first write, then you can do the Fisher projection formula. Now coming to here, that compounds which is optically active. we are telling that first that compound which has only one chiral center means it is linked with the 4 different groups, that is optically active. And if it is more than one optical chiral center, therefore it may be optically active or it is not, and it depends upon the various types of symmetry is present, yes or no. Means say plane of symmetry, center of symmetry or alternative axis of symmetry if present into the molecule, but the molecule has the chiral center but this molecule is optically inactive. But if it is not present, so the molecule is optically active. But various types of compound we can see that they has no chiral center but they are optically active. Say for example, if I take the system here, this one means it has more than one double bond is present, means it is the number of double bond that is in even. Okay, so therefore this compound we can see here, this compound it is the allyl compound and we are telling this compound is optically active but this compound has no chiral center is there. So why it is possible? Means it generates a non-superimposable mirror image compound, that's why it is optically active. Or we can say in other word that this compound has no symmetry is present, means no plane of symmetry, no center of symmetry, etc. These are not present. So this compound we cannot divide it into the two equal halves, means it has no plane of symmetry, or there is a no center of symmetry is present in this molecule, so it has no alternative axis of present into the compound. So therefore this compound is optically active. In other words, we can also say that this is its mirror image. So these two compounds they are mirror image to each other. But if you want to superimpose to each other, they are not superimposable. Say for example, if I want to this one, so you can see that my left side that is superimposed, but the right side is not imposed to each other. So therefore, we can say these two compounds they generate that the non-superimposable mirror image compound, and that is optically active compound. So what is the necessary condition for the optical activity for this type of center, that is the allyl types of compound? So if here that this is one side and it is one side, if the two side if it is linked with AB type, so therefore no symmetry is there. But if one side is AA or say BB is present, so therefore we can say this compound is optically inactive because it has the symmetry is present, mainly say plane of symmetry present into the molecule. Okay, so that's why we can say that the compound of the allyl type compound, if it is linked with AB or it is ABCD or it is BC like this, so therefore we can say this is optically active. Now here if it is only one double bonded compound, but it's linked with the 4 different groups, so this compound is optically inactive because it has a plane of symmetry is present, and this plane of symmetry that is according to the plane on the surface of this here. So if I cut the molecule, so the one half is the mirror image to the other, so this compound is optically inactive. But if it is a two double bond, so the one pi bond and the another pi bond, they are perpendicular mode for this compound. So that's why it behaves like say that is a chiral type compound, means it generates a molecular chirality generate and the molecule generates a non-superimposable mirror image compound. So that's why we can say this compound that the substituted allyl is the example of the optically active compound. And now we can also say that the substituted allyl and it will generate that the non-superimposable mirror image compound, and we can say they are enantiomer. Now go to the next one. So here we will substitute the double bond by the cyclic compound or one cyclic, one double bond. They are optically active. Now another thing that optically active but it has no chiral center. Say for example that the biphenyls. Now biphenyls when it is linked, so here it is AB. If the AB is a very big group and it is a different AB different and it is a very big group, so therefore the CC bond is rotates down to avoid the steric state. As they rotate down, so one benzene ring in the plane, another benzene ring, that is perpendicular mode, like this. So as it is like this, one benzene ring in the plane, another is the perpendicular. So the functional group, they are linked. So one is the up and down, another is the in the plane. So therefore they act as the chiral. They generate at the molecular chirality and is generated at the non-superimposable mirror image compound. So we can say this compound is optically active without chiral symptom. Thank you all.